Okay, thanks, Ted. Thanks for the opportunity to present here. My name is Jayanth Raman, and I have a double E background, and I have done some stochastic processes and so on, statistical learning quite a while back. So, and things have changed quite a lot. So this is all, a lot of it is new material to me, and so I hope to make it through it with your help. And yeah, so that's me. I'm interested in machine learning. I apply it now and then. I'm not a daily practitioner. I also have a software engineering background and experience, and so it's a combination of those. Yeah. So let's get started. I think I'm starting at 3.6, right, Roger? 3.5 is where you ended last time?
Yes. Yep. Yeah, that's correct.
So let me start sharing. Oh, it's saying something about security that I can't share. Sorry, I don't know why.
You should be good now, Jayanth. Are you?
Yeah, so I think it's on my system. I have to open system preferences and allow something, I guess. I have not seen this before. Sorry, give me a second. Otherwise, I have another computer and I can try coming from that. Okay, let me try again. Okay, it looks like I have to quit and reopen. I'll be right back.
Okay. And sorry, I gotta run my real quick errand. I'll be right back.
Okay. Are you able to see it now?
Yep, it's working.
Okay, great. Thanks, Ryan. Sorry about that. So yeah, so continuing on, 3.6 is hierarchical priors. And so we've seen priors before, and the idea here is that we don't know what to use as a prior, and so we introduce another level, if you will, and that is this set of parameters called psi, which will help us form the priors. And so the way I understood it is that, we have theta, the set of parameters that models our data D, whatever the observed data is. And then psi models theta. And so it's a level of interaction from psi to theta to D. And we can express the joint distribution as this using a chain rule, if you will. And so the last parameter, the last term here is actually P of D given theta comma psi. But I guess because of this theta being there, it's conditionally independent. And so you can just say D given theta. And so he says that this is used for cases where there are multiple data sets, all from the same area, if you will. And so he has given a couple of examples. One is sets of rats and studying diseases among them. And another is the performance of school children in different schools. And so they're all related, but I guess each data set is different, and you want to capture the differences in each data set by giving each set its own set of parameters, theta j. And we derive the theta j's from a set of parameters psi. One thing to note here is that all of the theta j come from the same set of hyperparameters psi. So if we define, let's say, a mu and a sigma of a distribution, from that distribution, we will draw theta 1, theta 2, and so on. And so he talks about all the theta j's borrowing statistical strength. In other words, getting things from different groups. And so that's the idea. There's also a comparison to what if you took all of these groups and made it into a single group and then computed parameters based on that. And there are some comparisons even on how dividing it into different groups compares with computing one set of parameters for the whole set. So there are some equations here where he says, okay, if it is an existing group, you can compute the output yj using this formula. You can see that there is no psi here. But if there's a new group, we can draw the theta stars from psi, and then you can compute the output, this new group from this. I don't see this application here. I don't know if anybody else did, but that's what he states. So so here's an example of a hierarchical binomial where you have, so this is the disease example. This leads to a disease example, I guess. So we have j different groups, and in each of those groups, there's a different number of individuals that fall sick or something, and then you want to model that. And the yj we derive from the binomial nj, where nj are the positive cases, and then the theta j is the parameters for that group j. We can talk about what I mentioned earlier, the pooled MLE, the maximum likelihood estimate, which is just the number of observed cases over the total number. So actually, I misspoke earlier. Nj is the size of the jth group. It's not the positives. The sum of the yj's is the number of positives. And so the MLE is simply the number of positives divided by the total size of all the groups. This is the pooled estimate. So this is what we would do if we would look at it as a single group. And the theta j, in turn, we want to draw it out of a beta distribution with parameters a and b. So the psi here is the a and b of this beta distribution. And so here's an expression for the joint probability distribution. And again, so given the psi, we need a prior for that psi. And in this particular case, he uses this particular prior for psi. And this psi is common, as I said earlier, to all of the theta j. Pictorially, it's represented this way. So we have A and B that are determining. So this is the beta distribution for A and B. The parameters A and B determine the individual theta i's, theta 1 through theta j, which then determine the yj. Also depicted here are the sizes of each groups. So n1 is the size of y1 and so on. So this is one way, A is one way to depict it. And I guess later on in the book, we would also be studying probabilistic graphical models. So we would see this representation again. And the same representation is also shown in what they call as the plate notation. So there is A and B, which is common to all of these individual theta j. So you can imagine that this plate is replicated j times, whatever is shown here in the bottom right. And you can imagine these connections, A and B, going to these each and every individual theta I, and each of those has its own size and its own output. So these are equivalent representations. So let's see. So we talk about posterior inference given that model, and I didn't quite understand where these Jacobians come from. I'm not too familiar with HMC, but he provides this where he looks at the joint parameters, which is all of the thetas and all of the psi. I also did not follow what these tildes are. If anybody knows, please speak up. And so he talks about the joint distribution between D, the data, and the set of all parameters, the thetas and the psi that determine the thetas. So we can look at the rats data set, and this is captured in this figure. So I'll go back to this figure. So here, what we are seeing is, okay, here are the number of positive cases. So if we sum up all the yj's for each of the 70 groups in this case, so some groups have no incidences of that disease. Some groups here have, 16 or so. And the other thing to note is that the sizes of these groups are also different. And so this is quite a challenging problem from that perspective. So you have some groups here with larger n of 50 and some under 25. And so we can compute a pooled MLE, and that MLE would show up in this, at this value of the red line, which is 0.18 or something. And if you try to do the MLE for the individual group, since there are zeros in the number of positives, for so the MLE is just, what is the MLE? The MLE is just the number of positives divided by the group size. And so you can see that the MLE for all these groups where there are 0 incidences is all going to be 0, and that's not very informative. But if you use the methodology given here, where you assume a psi that determines the theta, then you see that even for the cases where there are 0 incidences, we have a non-zero, posterior mean is shown here, but you have a non-zero value of theta. The other thing to note here is, this is shown in a forest plot. The HDI is nothing but the credible interval. And the credible interval is, so for the 95% case, you look at the projection of the distribution, and the thing that captures 95% of the area around the mean. And so it is drawn for these 70 different groups. And you can see the posterior, you can see the pooled MLE shown by this blue line. And you can see the individual group thetas. And his point here is that these thetas are drawn towards the MLE. So things that were out to the right are pushed inwards, and things that were out to the left are pushed towards the MLE by following this methodology. Any questions so far? Any comments?
Well, I don't necessarily follow all the math, but I mean, it seems to me that if you say, first we just did Bayesian inference, right? Mm-hmm. So if you have a prior and you have a likelihood, then you can calculate the posterior, right? But if you just basically make your likelihood more complicated and you say it's instead of just something based on theta, right? And you say, well, theta itself is based on psi, then all right, well, the math just got more complicated, but
right.
It's still the exact same process where we start with a prior, we have a more complicated double dependency kind of a thing.
Yeah.
You know what I mean?
Yeah.
So
yeah.
Like, I don't know, like, if you're playing Dungeons and Dragons and I tell you like, oh, roll, a D8 X many times. Well, like you can figure out what the distribution of like possible outcomes is, right? And if I say, well, instead roll this other thing, and it's going to tell you how many sides the die that you're going to roll is, and sometimes you're going to roll a 6, and sometimes you're going to roll 8, and sometimes you're going to roll 12-sided die. Well, I mean, it would take some work, but you could figure out like what the distribution of possible outcomes is.
Yeah. So yeah, you could even imagine like taking, let's say you have a set of 10 dice that come from the same bag or something, and you want to model all of them individually. They all share something because they probably came from the same factory.
Yeah.
But there are differences as well. And this method gives you a way to like model each of them differently, but also draw on the commonality of that factory.
Right. Yep. Cool.
Here's another example. This one is using a different model. In the previous case, it was a binomial. Here it is a normal, a Gaussian distribution. The theta j are the means. They all have a common variance, sigma squared. And here you can see, so I think the difference is you can see the difference between not using the psi, doing the computing the thetas using the individual groups, and using a psi between these two. You can see the difference here better than the other one. So the dashed line is the pooled MLE, and same thing here. The dashed line is the pooled MLE, and you can see that for each of these individual groups, they're drawn in towards the pooled MLE. One thing here, though, is that, because they all end up coming so close to the pooled MLE, you might as well have used the MLE. I don't know if there's a much difference between these. So it kind of is counter to that, but you do see the fact that they are pulled towards it in here.
Hey, Jayanth.
Yes.
If you go back to that one, so the raw data, that vertical line is the pooled estimate for theta, which seems, if I have to estimate, it's more like around 7.5. Is that right? Because so versus in the B graph, it seems to be around 5. So there is some variation or change that happened.
Yeah, I don't know. I mean, we can go to this schools thing.
No, that's okay.
Yeah.
Yeah,
But,
yeah.
Because each of these has its own Python notebook. Yeah, it is. So you're saying that this is not at 5, right? Yeah, maybe not.
No, it's not. That's what it appears to me, but the scale is different, right?
Oh, vertical. Oh, sorry. The vertical line here is the posterior mean. Okay. Sorry. So yeah, you're right. So in this case, it's the vertical line is the pooled MLE, and then in this case, it's the posterior mean. So I guess they have changed that. So it's drawn towards the posterior mean. Yeah. So, yep. The modeling here is on Gaussians, and so here your psi is the mu and the variance, and all of the theta are drawn from the same normal distribution. They apply this to the 8th school data set. We just saw that that figure. I didn't follow all of the math here, but the idea is the same. He also talks about like a non-centered parameterization for the data that we just saw, and the non-centering is that the theta j now is a combination of the mu and the tau, and then there is a noise type of component that is also drawn from a normal distribution. So this is another level of complexity, I guess, in the modeling. But as Ted said, once you put all this in, what flows out of it is what we saw before. The representation of it in the plate model is shown here on the right, where you have this, I guess this is eta j, added into the plate. So you have the mu and the tau in both cases. In this case, the mu and the tau determine the theta j. Here you have the mu, and not only do you have the mu and the tau, you also have an eta j that is drawn from a unit normal distribution. And
that eta is the noise term, is that right?
It's, yeah, I mean, I said it's the noise term kind of thing, but it's theta j equals mu plus tau times eta j. Yeah.
Right. So then each one's shifted a little bit to the right based on eta.
Yeah, it's shifted by different scaling of tau, essentially. Yeah, it's shifted to the right. I mean, it's not necessarily to the right
Oh,
because
it's not, yeah.
eta
could be
j
negative.
is, you know, a normal distribution, so you can get any value. Yeah. And then here it is, he shows the posterior for the 8 schools. And I was trying to see what we gain out of it. So here we see that everything is clustered together. And I didn't quite get like, why would this funnel shape be better necessarily than having all of them together. But it is a complexity in the way you can model things.
So, to me, it looked like that, what is that line number? Oops, scroll the other way. The main thing of this reparameterization was that line 36, where it reduces the dependency between theta j and tau.
Okay.
And that allows you to explore these other values of tau better, because otherwise they're too intercoupled.
Okay. Yep. Yeah, that you can see here. You're right. Yeah. Because you're plotting theta versus log of tau, there is, yeah, they're all tightly coupled here and less coupled here. Right. But why would that result in a better model? I guess you're just giving the model more flexibility. And then there's a small note about hierarchical conditional models. And I guess we will cover it later in 15.5 and 17.6. So that's about the hierarchical models. Any questions there? Any comments or questions?
I just had a comment about the term that he introduced in this section called shrinkage, which is essentially, which we noticed is how the posterior mean shrunk the variance in the theta, right? So apparently that term is used several times in this chapter, in this section. So yeah, just wanted to share that comment.
Yeah, thanks for that.
Yeah, so the way which you described, Jayanth, is like the groups regularize each other, and they term this phenomenon as shrinkage. And I think the other way to think about this is that the shrinkage basically is bringing the values towards the global mean, right? And there's more shrinkage for groups with smaller precision, which is like higher variance because of the smaller group size, which is the intuitive argument for using this approach.
Okay.
And there's more shrinkage if the precision is smaller.
Okay. Yeah. Great. Thanks. Thanks for those. Okay. Moving on. The next topic is empirical Bayes. And the thing about empirical Bayes is that, you know, rather than having to deal with a distribution for the psi, we just go for a point estimate. And that makes computation easier. And so so that's the main idea here. and
So
so he-
Jayanth,
yeah.
if I understand this right, if you pick a point estimate for your psi distribution, then you're back to just regular Bayesian inference, because once you've picked that point estimate and you've got like numbers as opposed to distributions, you plug those in, and now you're just left with theta as like normal sort of distributions, right? Maybe it's not exactly
Yeah,
the same, but you've eliminated a lot of the complexity because you don't have
correct.
theta conditional on xi. You just have theta drawn from a fixed distribution with numbers in for its parameters.
Yeah. Yeah. It's let me think. So it's like in the first case where your psi itself has its own distribution. And then once you get psi, then you can that in turn determines where you can draw theta from. In
Right.
this case, the first part is fixed. So
Yeah, like the very first
know.
example, right? Psi was a beta distribution, and the
Mhm.
thetas were binomials, right?
Right.
So to do the inference, you have to do this complex thing where you assume that the thetas are binomials and that they're drawn from some unknown beta distribution, right? But
Yeah,
if you just say, well, it's a beta 3,5, well, now it's not an unknown beta distribution. You
That's
just
right.
say, fine, I have thetas drawn from beta 3,5.
that's right. And then there is like, how do you pick that psi value?
Yes.
There's a couple of different ways of doing that.
Right. How you pick your point estimate.
Yeah. And you can either do a maximum likelihood one, or you can do a maximum a posteriori. And maybe there are other ways, but yeah, but that would be the way to pick these psi hats. And so he draws on increasing complexity in the models. So we can have an estimate of theta by just looking at the likelihood and then doing a maximum likelihood. We can introduce a psi, we can compute the posterior, and then compute the maximum a posteriori estimate. And then in this section, we introduce the psi hat estimates. And then also he has a comparison to the full Bayes.
Okay.
And so we go back to the rat disease model here. It looks similar. Same thing here. There are zeros, but in the posterior mean here we have non-zero values. This plot looks more spread out than the other one, because we're after all going for a point estimate, which is not as accurate as drawing from a full distribution. And so that's the difference I could see. So if I could quickly go back to the other distribution, you can see that this is a bit more tight. I just need to look at the scale actually. So 0 to 0.4. Yeah, it's a bit wider. So, but it looks a little bit more spread out.
So this is the one where we had the xi that was beta distribution?
This is the psi.
Right.
Yes. So let me go back, double check that.
Yeah, A and B is your beta distribution.
Yeah.
So then it seems to me that our point estimate ended up with a wider, flatter beta distribution. And that's why the thetas ended up being more spread out. I don't know if I know why, but I'm just saying, looking at the graph, as you noted, it's more spread out. So I think it
yeah, could be. And there's some math here to figure out the marginal likelihood. You can compute it directly. I think these are gamma functions. And here's an example. Here's the corresponding example for the empirical base for the hierarchical Gaussian that we also saw earlier. And one thing you can see that is a lot of these can be calculated. I didn't go through the calculations myself, but you can see that because of the point estimate, you can actually come up with, a closed form expression for theta j, and so on. And then he says, you can't use it for the 8 school data set since it has an unequal sigma j's. And then he says, go use the expectation maximization algorithm if you want to try it out. Markov models. So I'm trying to remember this thing. Yeah, so this is an interpolation that he introduces, deleted interpolation or back-off smoothing. So in the regular case, or in the previous case, you just look at the number of co-occurrences between j and k. And so you just have this one expression, njk divided by nj, I believe, right? So you're going from j to k, you see the number of j's, you see the number going to k, and that gives you an estimate of that transition. But here we also add another term that is solely based on the k, wherever you're going to. So it's almost like you want to see if you're transitioning from anywhere to k, what would be your estimate? And so you use that unigram frequency, and then you interpolate between the two using a variable lambda. And so he says, okay, now we can, whatever they did there, we can interpret this as an empirical Bayes approximation. So I've seen this in later on also, we will see this is like, for example, for the leave one out or something, it's like, okay, this is what people do, and here's a Bayesian interpretation of what is being done there. And so I guess this also, I kind of read it that way. I don't know if other people see it that way, but yeah.
Yeah, so I didn't work through all the math in this section, but I've definitely seen where people use n-gram models. I've been seeing where, like, you have a language model and people would say, well, let's, as a baseline, compare it to like a bigram model or something like that, right? And so if you're doing your standard Markov chain solving thing, when you have zeros in transitions, then that causes a problem.
Right.
And so you can do this thing where you just add 1 to the to all the numerators, and then based on however many ones you're adding, you need to add that many to the denominator also, so that it, in the end, all of the fractions still sum to 1. Okay, cool. But that's not very principled. That's just sort of like and look, they're not 0 anymore, right? So then earlier in section 2 or whatever, they said, oh, this actually is, I think, like a uniform prior or something like that.
Okay.
You can do the Bayesian interpretation of this +1 business you did, this Laplace smoothing, as like a uniform prior. They said, but a uniform prior is not very intuitive. Not all words are equally, and so then this is using a non-uniform prior on the word probabilities, and then you get this gnarly thing that, again, that I couldn't follow all the math, but
yeah,
it makes sense then that you would get something probably a little bit more realistic, because transition to the word whatever, the or you is going to be a lot higher than transition to the word ukulele or something like that.
yeah, and just to add to what you said, if you already have transitions between bigrams, then you would have the first term coming into play, and if you didn't have it, it's only the second term that would come into play. And then he says, well, but the question is, how do you determine lambda? He says, just use cross-validation. So I guess you try out different values and see which works best for your data. So he kind of falls back to a frequentist approach here a little bit. So yeah, I also didn't follow the math, but that was the gist of it. And he says that there are better models. This one doesn't beat the state of the art, and then there's this other model that is better than this one. And then there is non-conjugate models, which makes it even more complicated. And again, we go to a variational EM method, and we punt this to section 10.
Okay, so when we get to variational inference, then they're going to, I think, I didn't understand this, but now that you just said it, I think I understand. So we have a closed form formula that we can figure out what the point estimate is if we have these conjugate distributions. But when we don't have that, then we have to go to approximation. And so section 10, I assume, is variational inference. And so that's when we're going to run into it.
Yeah, must be. Yeah, I don't know, but yeah. Must
okay.
be. Yeah.
Cool.
Yep. So that concludes empirical Bayes. Any questions, any comments on that? How is it overall, by the way? I hope there is some information gain in what I'm presenting.
And from the discussion as well.
Oh, yes, of course.
I'm curious there with sorry, somebody speaking. What is the state of the art language model? Is that the ChatGPT, or they're referring to something else?
No, this one is the n-gram bigram model. And I think they're talking about the state of the art in that bigram setting. And, this is from like 1995 and 1998. And so that's what.
Okay, so it's a different.
Yeah.
Oh, thanks.
Yeah, so we are not into the transformers, the neural networks, and all of those machinery.
But part of why we're reading this book is because we want to get to his Bayesian understanding for like diffusion image generative models and some of the Bayesian interpretation around like large language models and neural networks and stuff. So yeah, so
yeah.
that's part of the reason why we're slogging through all this stuff.
Oh, it's helpful. Thanks.
Okay, model selection. So this is, of course, a famous saying: all models are wrong, but some are useful. by George Box. And so we come across like, how do we pick between models? And this goes into cross-validation, things that we would, most of us would have seen before, but this provides a Bayesian setting for that. So we start off with trying to apply the Bayesian method. If you have this funny looking M, calligraphy M, number of models, how do you pick that? If you're able to imagine a distribution, given the data, if you can plot a distribution of all the M's, you want to take the most probable model. So if this is the, if you can imagine that this is the posterior, you can say this would be a map estimate of it. So I didn't quite, I can't quite relate this to like numbers and so on. So this is a little bit hand wavy maybe, because, if you can imagine, imagine that you have all the models, how do you order them along the axis and so on? But in a hand wavy way, you can imagine that if you can draw this distribution, you want to pick the maximum value and say that's the model, that's the best. Here's your expression. This we have seen before, except that, we would have seen, instead of the M, we would have seen thetas or hypotheses or something else.
Hey, sorry, Jayanth, can I say something about your last comment?
Yes, please.
So if we stick with like really simple models, okay, so let's say we just had a couple different linear regression models and we solve them all with maximum likelihood, then we actually have actual likelihoods for each of the models. And so we could say like which one has the largest value there. We could do the argmax.
Yeah, this also talks about a distribution of the M. So it's like P of M given D. And so if you can imagine a distribution where M is on the x-axis, and then you draw this distribution, you want to go for the maximum.
Yeah, I don't know if M needs to be continuous or if it can just be discrete, but
yeah, it can be discrete. It can be discrete, and then you can pick the one that is the maximum. Yes,
right.
And they can be very different things. They don't all necessarily need to be linear. For example, you could compare.
Right. No, but I'm
with,
just saying like a really simple one that I know is that you can solve linear regression with maximum likelihood, and then you actually have a number that is the likelihood that you found the max of. Right.
True.
So if you're predicting whatever, like kids, 6th graders test scores, and you could say, well, I'm going to base one based on this data, what grade they got last year, and blah, 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 blah. And then I'm going to build another model that's based on how they did on the quizzes and how tall they are. And I'm going to build another model based on what color hair they have and what color eyes they have, right? Each of them can be, the linear regressions can be solved with maximum likelihood, but then you could say, oh, the likelihood of the whatever, the hair color model wasn't very good for my data.
Yeah.
And 9, 15, and 16, Jen, to your point, they do assume or make a statement that the prior over models is uniform. So so it's like equally likely, right? Then it makes it much easier to address that distribution.
Right. And there's also, like if you don't make it uniform, then what knowledge are you basing that, that value on? Or are you biasing it in a certain way? Yeah. And
sorry, just wanted to add that and if anyone here with the physical sciences background, I've seen more often than not that there's a reliance on or a tendency to use Gaussian more often than not for the distribution model for the natural processes, or sometimes even exponential, depending on the kind of processes there are. But other than that, I don't know what other biases can come in for the model selection. So we don't know.
Yeah, so and the easiest thing to do is to say it's they're all equally likely. I just want to also point out that M can be any model. M can be, you can be comparing linear to logistic to quadratic to a neural network to SVMs to whatever you can think of. You can throw all of it in the soup and try to apply this equation.
All right, I said something, but I probably shouldn't have. So I'm gonna nudge you a little bit to say let's keep going. Let's see if we can actually finish the chapter.
Yep. Okay. So we have like half an hour. Yep. And yeah. So let's see. So okay. So here's an example where we compare two models, M0 and M1. I think this was a slightly interesting example. Actually, before I get to that, he also talks about the Bayesian Occam's razor, where it's like, okay, what is the right model? And so that is shown in this particular figure here. So if you assume that D0 is our data of interest, and we're comparing three models, it could be that we have a very simple model M1 that doesn't quite capture the complexity in D0. And so you can see that the probability of this data given the model M1 is close to 0. If you go for a very complex model, which is shown in green here, the M3, actually, before I go to M3, let me cover M2. So if you go for a slightly more complex model, it could cover the data D0, and you could get a higher value for P of D. If you go to a too complex a model, then the complexity of the model is spread out across many different data sets. It can handle this data set D0, it can handle even more complex data set D0. So you're kind of leaking, some of this capacity into these other data sets, and you lose out from what you could have gained by using this model M2. And so this is what he calls as the Bayesian Occam's razor, and it's more like I call it Goldilocks. It's just M2 is the just right model. And of course, this is all hand wavy and theoretical, and I don't think that there's these blue lines is all probably hand drawn, but I think the idea is very interesting. And so, okay, so this example here, comparing M0 and M1, we're comparing M0, which assumes a unbiased coin, and then another M1, which assumes a biased coin. And so in the unbiased coin, suppose we have n flips, we can see that the probability of the data is half to the power of n. Everybody agree with that? That's easy. This one, if you assume a beta prior, so this also I think we've seen before. We have the prior alpha 1, alpha 0, and if we observe n1 heads and n0 tails, it shifts this way. And so we want to compare these two. And so he has plotted it, but I think maybe later on he does it. But I've seen people also compute a ratio of the two. And so you can, like you do comparisons using ratios, you can you can compute a ratio of these two. You will also have a term that that involves the prior for the model, and there you can, there you can assume that they are the same, or you can add your own spin to it. That would be another way to do it. But in this figure here, he's plotting. So what we're seeing here is, okay, so we let's say we fix n to 5, and he's shown all these things. So what is shown here on the x-axis is there are 2 to the 5 different variations in which you can get these coin tosses. There's only one way to get all tails, one way to get all heads, and then there are these many ways to get just one head, and so on and so forth, right? And so if you compute using that equation up here, if you compute log PD of MI, you get these very low values for 2 and 3 heads, and then higher values for 1 and 4 heads, and then really high values for 0 and 5. So what this is saying is that, you have a biased coin. And if you did, I drew this line, by the way. I think this is right. You can double check this dark blue line. He doesn't have it in the figure. So this would be the unbiased coin. And so you can do a comparison of M0 and M1. In the cases where you get 2 and 3 heads, which one would you say is more likely, unbiased or biased? According to this model, it's like the unbiased one wins. In these cases, if you end up with 2 and 3 heads. If you end up with 1 and 4, the M1 is slightly preferred over the biased one. But if you get 0 and 5, no heads or all heads, then you're like, oh yeah, what are the chances that it's biased? You'll say very high, right? And so that's what this is kind of depicting. And here's a diagram showing using the Bayesian information criterion, which I think is also covered later. So I'll keep moving. And so this is trying to explain ensembling using a Bayesian setting. And so you can compute. So given, you can write this from a mathematical perspective. You can say, okay, if you have all these different models, and each of them you can predict Y given that model, you're getting that model given the data, then you can combine them all using this. The difference is that in ensembling, we come up with equal weights or what have you. The difference here is that the weightage is dependent upon how good the model is. And so P of M given D, again, this is a little bit, I don't know how you would compute it, so it's a little bit hand wavy for me. But if you imagine it, then yes, of course, if you have one model that's doing really well, the weight for that model will be really high, and you would pick whatever that model is outputting compared to the other models. That's the idea. Okay, so I didn't go through these particular sections in detail.
Yeah, so maybe let's just blitz through 3.83 to say, here's some techniques you could use to actually not be completely hand wavy and try to get some numbers for your different models such that you could do the stuff he talks about.
Yeah, okay. There's a mention of elbow, which I think we will see later. He does try to connect cross-validation and marginal likelihood. So he divides the data and he says, you don't have the nth fold, if you will. So that's the D minus n. And then here's a way to define it. This one is a leave one out. So you have like n different folds where you're leaving just one sample out. And here's a mathematical representation of it. He talks about a log marginal likelihood. You get this, and this is from this particular expression, the chain rule in probability. You can come up with this expression. Here is where he uses a point estimate. You have the delta function, and you can simplify it this way. Talks about conditional marginal likelihood. The marginal likelihood, he says, is what is the likelihood of generating the training data from my prior? But the conditional marginal likelihood is what is the probability that the posterior could generate withheld points from the data distribution. So the conditional marginal likelihood is where you kind of chop off, you ignore the first k-1 terms. If you can see here, these estimates might be very high because there's not many data in play. And therefore you're like, okay, I'm just going to ignore these first k-1 terms and then just use the rest of it. That's what this is trying to do here. And if you set k equal to n, then you have one of the leave one out. I think this should be k equal to n and not n-1. You will have one leave one out. And if you average over all orders, so basically you manually rotate them and then you reapply this, then you can get the full leave one out estimate. So there is another setting for the leave one out estimate. So this is the Bayesian way of doing it. So what we saw earlier is fitting the Bayesian methodology to what people already do with leave one out. Here it is, well, if you wanted to start, start afresh, how would we do it? Here he talks about like using Monte Carlo simulation where you get S different samples from your distribution, and then you come up with I guess an average of those different values. So here's an expected value of that methodology. And this, I did not go through this particular math. He talks about even more complex models using a Pareto distribution. I didn't quite understand why you would do Pareto and not something else. But I guess if you read these papers, maybe it will explain it. So here he talks about 3 different information criteria. I think some of this is regularly used in statistical inference. MDL, the minimum description length, the Bayesian information criteria, which uses the number of samples that you have, and the AIC, which doesn't use the N. And here's a derivation of like, how you can get to BIC using a Bayesian approach. And the loss here, basically you're penalizing complex models, which have a large N in it. And yeah, so that's a comparison of these 3. There's one more actually. WAIC, which uses the C of M term. I don't know if I quite followed everything here. So yeah, so that is section 3.8. I don't know if there's any questions there. So I think I have two more. Is it?
There's a little 11 also, I think. So
Oh, little 11. Okay.
we need to
So I don't
somehow.
know if I made it to 11. So this is all like super thick material. I tried to get through as much as I could, but it's still pretty involved. So model checking. So I'll keep going. Model checking. So this is of a single model. So if you're given a model, can you tell, is this model good, or good enough, or too bad, or what is it? So so let's see here. So he defines a test metric test of D. You generate multiple Ds, multiple data points, and then you compare your test metric for this D with the individual with the tests for the individual Ds that you have sampled. And if there's a large difference between test of D and the individual test of DS's, then you say, oh, this is probably not a great model. But if they all align, then you might have a reasonable model. So that, I believe, is the general idea here. And the metric you use, the test of D, he talks about a couple of different scenarios here. One is using the minimum value, another using variance. I think you can see this in this diagram here, where the speed of light was measured. There were some 66 samples. And if you put up the histogram, it looks like this. You can see that most of the values are here, but there are a couple of outliers, one at 0 and one at -40 something. And the question is, how do you, like, if you have a model, is your model good enough? And so if you do 9 samples, let's say you come up with a model and you do 9 samples of it, you can see that the model that you came up with doesn't have the outliers. So if you compute the minimum here for each of these, you end up with a distribution like so. And the actual minimum is -44. So what you're doing is not capturing the minimum. And so if your metric is the minimum, it's difficult for you to model it, or these models don't capture it. But if you're doing the variance, you can see that, here's the true variance in the red line, and what you have modeled all fall around it. And so therefore, your model is able to capture the variance of X. So that's what this is showing. Here's another example using divorce rates, marriage rates. And here's a linear model. Here's some outliers. There's an interesting comment he makes about Utah and Idaho. So let's see. So yeah, so I think what he was able to do here is draw these error bars around this, around these data points. Okay, so we talk about p-values here. There's a comparison between a Bayesian p-value and the classical p-value and the frequentist p-value, where we are, in the frequentist case, we are observing the sampling distribution to a null hypothesis. So that is a little bit hypothetical. So we don't have a dependence on the data here. If you look at the equation, you're looking at the test statistic that is at least as extreme as your data, and so this is, you are considering your data as well. 3.25. I forget why I put this comment here. Yeah, so he says in in that figure, the Gaussian model is capable of representing the variance in the data, but it is not able to represent the range or the minimum in this case of the data. Okay, so keeping on going, hypothesis testing. So this is the usual frequentist way, right? So one of the test statistics, he's a bit critical of the frequentist way. He says there's a zoo of test statistics. Then here's a commonly used one, where you assume a mean of the null hypothesis. Usually it might be 0. Then you compute your test statistic. Let's see. So I'm forgetting some of these things. So in the Bayesian approach, you compute the Bayesian factor, the thing that we looked at earlier between the two coin tosses, M0 and M1. You can compute the ratio, and that ratio gives you the Bayesian factor. And this to me looks a little bit like a bit of a heuristic in terms of saying, okay, if it is less than 1/100, then decisively you can say M0 wins. If it's over 100, then M1 wins. How do we come up with these numbers is a little bit iffy, but anyway, there is a methodology here in terms of comparing two models and computing the Bayes factor. Yeah, so here is the actual equation of the Bayes factor. So we saw this earlier with the coin toss. You can see the priors here. We had the discussion earlier about how do we assign P of M1 and P of M0. If you assume that they are all equally likely, this term goes away. And you're just left with what your model did with the data. He talks about improper priors. And I didn't quite get through all of this, the marginalization paradox. One of the things he talks about is if you want to apply this Bayesian hypothesis testing approach, then it is more computationally intensive. than the other case. And I don't think I followed this, the binomial test. A two-sample test is the chi-square test. We draw from a binomial of theta j. Theta j is in turn drawn from a uniform prior here, beta of 1 of 1. And then we're trying to figure out if the theta j is the same. So theta 1 and theta 2 is it the same for all the groups. So I'm sorry I wasn't able to get to any of the details in these sections later here. If anybody else has gone through these sections in more detail, please feel free to add to this.
So I have not read ahead to the whole book, but I don't think we're going to use these in the later chapters.
Okay.
So
Yeah, it felt like it was just dumping a lot of terms and concepts without really, a context with how we're going to use them, how they're applicable. I found it very difficult.
I interpret it as, if I'm going to be a proud Bayesian and poo-poo frequentist statistics, then I need to at least include in my book something that says, well, what would you do instead of the kinds of hypothesis tests that they would do in frequentist thing, right? So you have to at least show the alternative. And so this is the alternative with its Bayesian background, explaining the principle behind it.
Yeah, yeah, like I said earlier, I got a little bit of that also. Is like some of this was even trying to retrofit, like, okay, you're using leave one out, here's a Bayesian interpretation of it. And here's a better way to do it by doing a Bayesian leave one out. And so on. Yeah.
So I could be proven wrong, but I don't think we need the hypothesis testing. So hopefully this Bayesian foundation from chapter 3, we've got enough of it that now we're going to start turning that Bayesian crank and using this in the later chapters and the different models and things like that.
Mm-hmm.
So, but again, I'm not sure, not having read the whole book. There are probably certain sections that are fundamentally based on Bayesian inference. And there are other sections where the author might, again, do this thing that says, like neural networks, like just imagine like a single hidden layer, fully connected neural network, right? It's its own thing, but let's just apply this Bayesian interpretation to explain what's going on there. You know what I mean? So I think there's going to be two different kinds of concepts. The concepts where he just says, this really is fundamentally the math is based on Bayesian, and then the other ones where he just backs into a Bayesian explanation.
Yep.
Yeah.
Yeah. So I'm sorry I didn't cover 3.10 very well. If you want, I can try to do it another day, or we can say, as you said, Ted, that we can come back to it if we need to.
Yeah.
Yeah.
I'm good with
agree.
that. If we need to.
Okay.
Did anybody have any
Yeah.
specific questions from reading this? Anything particular that stood out that you had a question about? All right, cool. So then we're at time, but let me just say, so next week, Dave has volunteered to take us into chapter 4. Have you peeked at chapter 4 at all yet?
On and off, and I mean, I've done some of it in the past, but not thoroughly from this book.
Okay. So yeah, so I've been pretty busy with work. I haven't really peeked at chapter 4. I've actually peeked more at other random chapters just because there were different topics. So again, we all know this book has a lot of math. It's quite dense. I, for one, am not expecting to understand everything. I'm hoping to understand more than before I read it, and then enough that later on, if we're using it again, I can go back and reference and repeat and strengthen. So the goal, Dave, will not be to take us through. I know we chapter 3 we tended to do it, but the goal isn't necessarily to take us through page by page, section by section. It's more to say, let's make sure we understand the concepts and see if there are questions, stumbling blocks. And certainly in my case, that there are times when there's subsections that I just write it off. I just say, okay, I'm going to take on faith that you know what you're talking about, and there's something here. And if it turns out to be really important for, like, you know, some technique, like I got to understand this section to understand variational autoencoders, then I will at some point go back and spend more time. But there's just, you know, I think there's just too much material for us to really go page by page. If that helps, so that you can, you know, kind of pick and choose your battles of the stuff that you really want to highlight from chapter 4. Does that make sense?
You know, at some point I read Proust, and I had a very good foreword for this. A warning from well, forward was very good about that. The idea don't count much on the plot, just enjoy the view. So, and I was trying to understand, you know, what is the practical meaning of all of it, but it looks like, you know, I just should enjoy mathematics.
Yeah, I mean, that's my approach right now, is just enjoying the parts that I can relate to, that I can connect to something like the bigram model. I was able to connect to stuff I've seen, you know, and again, I'm perfectly happy if we get to a really interesting topic like, you know, variational inference, you know, diffusion models, where we say, wow, this is building on math that was in section 3, chapter 3, or something that maybe at the time we went quickly, and we'll revisit, you know, those particular subsections because they're like really, you know, getting used. But yeah, there's just so much stuff covered here that I don't know if it's really going to come up again. So we're gonna, yeah, enjoy the view while we can, and keep moving to see if we can get to the next the next view.
So what I've noticed is, you know, when I'm assuming this is why his book is coming up with a new edition or a new version every few months, is, as I'm assuming, adding more topics. There is reference to some topic, whether it is a newer evolution to the foundational topic, or maybe he feels the necessity to add more details. So hypothesis testing is referenced very few times in the later part of the chapter of the book, but maybe when he added it, he felt necessary to add the context. And then once you add the context, wanted to make it sufficiently large, which maybe the mathematicians or the theoreticians would appreciate.
Yep, that makes sense. So we as readers can choose to say we're going to kind of go faster through certain sections, and then, you know, I'm okay, fine. So let's just say we blitz through section 4.3, but later on we find that it's really useful for some model we care about. We can always go back. You know, it's not an irreversible decision. So that's where, yeah. All right. Well, thanks guys for joining us again. And also we had the new Zoom procedure. So if you guys are okay, we're just going to keep this procedure, and again, it means that somebody who halfway through our meeting, if they just stumble on the meetup link and they click the Zoom link, they're going to see that it requires a password. They could go and get it, but we think, you know, that Zoom bombers are sort of less likely to just take the extra 30 seconds it would take them to do that, and more likely to just move on somewhere else. So if there's no serious objections, we'll just keep this procedure. And like I said, you're welcome to try the same password next week. And there's a decent chance it'll work. But if for any reason you try and it says the password's not valid, just then go to Slack and you'll see there may be an updated password. All right. All right. Thanks again, Jayanth.
Yep.
Yeah, Jayanth, thank you.
Yep.
Really appreciate all the discussion leaders, and we'll keep going next week.
Yeah, and thanks to everybody for adding as well. Appreciate it. Yeah.
All right. Have a good week, everyone.
See you next week.
Bye.
Thank you. Bye-bye.